So as we have seen the definition of pointwise convergence, in that n0 which we have, it was depends on epsilon as well as x. So under the uniform convergence, that n0 which we have learned or which we have got, it only depends on epsilon. So let us give this definition of uniform convergence. Let Fn be a sequence of functions with the domain E. We say that the sequence Fn converges uniformly if there exists a function f with a domain D, domain E, such that for given epsilon greater than 0, we can able to find an n0 depend on only on epsilon, not on x, but not on x, such that mod of fn of x minus fx is less than epsilon for every x belongs to E and for every n greater than or equal to n0. In this case, we can write is limit of fn of x is fx as n tends to infinity uniformly. So you have to mention whether this convergence is uniform or it is pointwise. So obviously one thing is clear, that every uniform convergence is pointwise, but the converse is not true. Okay, so that we can write as a note that uniform convergence implies pointwise convergence, but the converse is not true. What is the example which we have discussed in the previous lecture? That was fn of x will be x upon 1 plus nx. Fn of x is x upon 1 plus nx if your x is between 0 to infinity. Then in this case, your epsilon pointwise, sorry, this is not example, this is uniform convergence, yeah. But in this case, fn of x is equal to x power n, x you're between 0 and 1. In this case, we have concluded in the previous lecture that it is pointwise convergence, but the epsilon which we got, it depends on n, that is n0 and x. So this is not uniform convergence. So the converse of this result is not true. Okay. Now immediate result on the uniform continuity is called the Cauchy's criteria. Okay. So this is the result, Cauchy's criteria. So let us discuss that result. Let Fn be a sequence of real or complex valued function with the domain T. Then prove that the sequence Fn is uniformly convergent if and only if for every epsilon greater than 0 there exists n0 belongs to n depending only on epsilon such that mode of fn of x minus fm of x is less than epsilon for every n m greater than or equal to n0 and for every x is in E. So it's like a Cauchy sequence. If you can talk about the sequence of numbers, then it is a Cauchy sequence kind of thing. So this is known as a Cauchy criteria. It says that the sequence is uniformly convergent if and only if it is a Cauchy, because it is a real valued and a complex or a complex value, and both of them are, we know it is a complete spaces. That's why we have. If you want to generalize this result, you can just think of that how to be generalized for in general any sequence of function from x to y, okay, where x and y are the metric spaces. So you can talk on this. But here our objective, or we restrict ourselves with the real valued function or a complex valued function. And this result is if and only if. So I'll start with this side. Suppose that Fn is uniformly continuous, sorry, uniformly convergent. F in E. Suppose that it is uniformly convergent in E. Then as per the definition, what we can say, by definition of uniform convergence, for epsilon greater than 0, there exists n0 belongs to n, such that mode of fn of x minus fx is less than epsilon. We'll adjust this epsilon later on. Okay, for n greater than or equal to n0, and for every x is belongs to E. And I've called this inequality or this statement as one statement. Ultimately, how to prove this? Mode of fn of x minus fm of x is less than n. So now I'll start with if n is greater than or equal to n0 and any x, it is between E. Start with this fn of x minus fm of x. Adding and subtracting x from here. Fx. By triangle inequality of a real number or complex number, we can say that is fn of x minus fx, and due to this modulus, we can say that this is fm of x minus fx. So if I want to use this statement 1, then n is greater than or equal to n0 is there. M is also greater than or equal to n0 is there. So for that it is epsilon plus epsilon. So if I don't want to write epsilon, 2 epsilon, I just adjust by 2 here. So this is less than epsilon by 2 plus less than epsilon by 2 because of 1. And this is true when your n is, so that we already have here. So hence what we can say, every epsilon greater than 0, that exists n0 belongs to n, such that mod of fn of x minus fm of x is less than epsilon, where this n0 depends only on epsilon. Due to this n0 is depends on this n0, and under the uniform convergence, this n0 is only depends on epsilon. For every n greater than or equal to n0, and for every x is v. Now, converse part. Let's suppose that given epsilon greater than 0, there exists number n0, there exists a number n0 belongs to n, depending on only on epsilon, such that mod of fn of x minus fm of x is less than epsilon for every x belongs to E and for every n greater than or equal to n0. Accordingly, this is the statement 2. So this will say that this sequence fn of x is a sequence of number, and since this each fn's are a real valued function or a complex valued function, this sequence, the sequence fn of x is a Cauchy sequence in R or C. And we know that this R and C, both of them are complete metric spaces. Since R and C are complete metric spaces. Since they are complete metric spaces, we can say that this fn of x is convergent in E for every x in E. Therefore, this is the point-wise convergence we can have. Therefore, we can say that fn of x is converse to fx point-wise for every x is in E. If I call it, this is the statement 3. So as per the definition of this point-wise convergence, we can say that for each x in E, there exists n0 belongs to n. This n0 might be depends on that. So that is mod of fn of x minus fx is less than epsilon for every n greater than or equal to n0. All this is the statement 4. Now, take n is greater than or equal to n0. We'll start with fn x minus fx. That is equal to fn x minus fmx plus fmx minus fx. This is less than or equal to fn x minus fmx plus fmx minus fx. So to adjust this, I will say this is epsilon by 2. Here is also I may write epsilon by 2. So that's why this is less than epsilon by 2 plus epsilon by 2, this is equal to epsilon. Hence, Fn is converse to F uniformly. This completes the proof of this. Also, there is another example which is very interesting. So every time if you want to check whether the given sequence of functions is uniformly or not, then you have to looking at whether that n0 is depends on epsilon or x. So with regards to that, this theorem is there, and it will reduce our work to checking whether the given sequence is uniformly or not. So suppose that limit of n tends to infinity, fn of x is fx for every x is in E. That means it is a point-wise convergence. Okay, and let a mn will be the supremum of mod of fn of x minus fx. X belongs to E. Then prove that Fn converges to F uniformly if and only if a limit of Mn equal to 0 as n tends to infinity. So this result is very interesting. That it's, if you want to prove that this each Fn is converges to F uniformly, if and only if you have to show that this Mn is tending to 0. That is the supremum of Fn minus Fx. Let us try to prove this statement. So suppose that Fn converges to F uniformly on E. This is there, given. So as per the definition, for given epsilon greater than 0, there exists n0 belongs to n, depending only on epsilon, such that mod of fn of x minus fx is less than epsilon for every n greater than or equal to n0 for every x belongs to E. Now since this n0 is depends only on epsilon, I may take supremum, so not having any changes. So that is, I am taking the supremum both sides. So this will give you supremum of mod of fn of x minus fx less than epsilon as x belongs to E. But what is the supremum? As per our definition, this is Mn less than epsilon, and this is true for every n greater than or equal to n0. This is also true for every n greater than or equal to n0. So therefore, I can say that Mn minus 0 is less than epsilon for every n greater than or equal to n0. So what we can say is, for every given epsilon greater than 0, there exists n0 belongs to n such that Mn minus 0 is less than epsilon. So this will gives you that hence a limit of Mn is 0 as n tends to infinity. Now converse part. Conversely, suppose that a limit of Mn is 0 as n tends to infinity. What is given? The given is the sequence is pointwise convergence. So as per the definition of this, we can say that for given epsilon greater than 0, there exists n0 belongs to n such that mod of Mn minus 0 is less than epsilon for every n greater than or equal to n0. So this will give you supremum of fn of x minus fx is less than epsilon for every n greater than or equal to n0. But this is the supremum. Okay, and supremum is always smaller than each and every individual. So that is, sorry, it is bigger than each and every individual. So that is, I can say fn of x minus fx is less than or equal to supremum of fn of x minus fx, as your x is in E less than epsilon for every n greater than or equal to n0 now, and for every x is in E, we can say. So this is less than epsilon, so that will gives you limit, or I can say fn is converse to f uniformly on E, and this completes the proof of this statement. So whenever now you want to check that any sequence of function is uniformly convergent, then you have to do, so I can writing the working rule to check a uniform convergence. The first things you have to do, step number 1, find whether it is a pointwise convergence or not. Or you can find the limit of the function, limit function, whatever the limit function is there. Barabar? And the second is to find what is Mn. What is Mn? Is the supremum of fn of x minus fx. And third one is to evaluate this limit of Mn equal to 0 as n tends to infinity. Check whether it is 0 or not. If it is 0, then it is convergent, uniformly convergent. This sequence fn is uniformly convergent. If it is not 0, then it is not uniform convergence. It is only pointwise. If it is not pointwise convergence, that means the limit is not exist. There is no chances to having the convergence. So these are the working rule to check whether the given sequence of function is pointwise convergence or uniform convergence. So we can solve certain examples based on this uniform convergence into the next lecture. Till you have any question, you can ask.